Everyone, welcome back to your channel. In this video, we will be discussing about the last problem of today's weekly contest, minimum score after removals on a tree. So we are given a tree and we have to find out the minimum score of the tree. What is the score? Score is defined as the difference between minimum and maximum XOR of if we divide this tree into three connected components. So for example, let's say this is the tree and we divide this tree into three components. First component that contains 1 3 and 4, second component which contain only 0, and third component which contain only 2. Now the what is the XOR of this component? The XOR will be 5 because there is only one element or one node here. This what is the XOR of this component? It contain only one node, hence the XOR will be 1. What is the XOR of this 1 3 and 4 component? The XOR will be 5 XOR 4 XOR 11, which is 10. So we get the XOR of these three components, 10, 1 and 5. Now what is the score of this configuration? The score will be the maximum minus the minimum, which is 10 minus 1, 9. So score of this configuration, wherein the first component will be having 1 3 and 4, second component will be having 0, and third component will be having 2. The score of this particular configuration is 9. Similarly, for all such configuration, you have to find out the one with the minimum score. So that's the question. Now, how to solve this? First of all, let's discuss how to get a component. So in a tree, if you remove any edge, let's say we remove this edge. If you remove any edge, you will get a component. So if we remove this edge, we will get two components. For one component that will contain this entire thing, okay, uh, and second component that will contain this entire piece. So if you remove any edge in the tree, you will get two components because every edge is actually connecting something. Like there is no cycle in this tree, so that's where every edge is actually a bridge. So if you remove this, you will get at least two connected components. So we have to find three components, right? So in a way, we need to remove two edges. That way we will get three components. Let's say we remove this two edge. So the components would be this, and the remaining piece, which is this. Okay. So hope you get what we are trying to do. We have to find three components, and what we have just discussed is removing any two edge will give us removing any edge will give us at least two components. So we will remove two edges, and hence we will be getting three connected components. So now we have total n number of edges, right? Like n minus 1 edges, so order of n edges. So we have to choose two edges out of this n edges. So how many ways you can choose two edges? N square, right? So the value of n in the problem is 1000. So n square will work. But after choosing these two edges, you need to find out the score as well for this particular configuration. The configuration where this is one component, this is second component, and the third one is the remaining component. So to find out the score, you actually can't iterate over the entirety all once again. So if you want to iterate, you can easily find out the score of each of this component, but you are not allowed to iterate, because if you iterate, the complexity would be multiplied with n, because basically you get all possible combination of edges, and then you iterate over the tree to find out the score, and hence this n. So this complexity would not pass, because n cube is something that is that will not pass as per the time complexity. So in a way, what you need to do is you need to find out the score of a particular configuration in just order one time, or less than order n time. It can be log n as well. So how, like, that you have to find out the XOR of these subtrees, right? So there is no way you can find out the XOR of a subtree in order one time without having some kind of pre-computations. So we are sure that we need to do some kind of pre-computation, and after doing pre-computation, we should be able to answer what is the score of a particular configuration. And what is the configuration? Configuration is, given that we remove two edges, what will be the score of the connected components that will be formed by removing these two edges. So our problem now reduced to finding out, like finding an efficient way to find out the score of a given configuration. So let's try that problem instead. So first of all, let's say that this is we remove this two edge. Okay, so we have to remove two edges from our entire graph, from our entire tree, right? So what are the possible scenarios wherein you can remove these two edges? So first of all, let's say you remove two edges which are in different subtrees. So you remove this two edge and you will get a component like this, and you will get a component like this. Okay, so this, like will you be able to find the score of this particular configuration? Basically you have to find out the XOR of this, XOR of this, and the XOR of remaining elements in order one time. So first of all, these two are pure subtrees, right? Like this two is complete subtree of 3, complete subtree of 2. So if it is a complete subtree, finding out the XOR in the entire subtree is very well known problem. You can directly do DFS starting from this and find out the XOR. We will look at an example for that, but finding out the XOR of a particular subtree is easy. So you can easily find out the XOR of in the subtree rooted at 2, and you can also find out the XOR of subtree which starts at 3. Now let's say you get the XOR at A and B. Okay. Now how to find the XOR of this in order one time? Basically this can contain any configuration. Like this is not a pure subtree. Like this, if you look at this configuration, this is not a pure subtree. This can be a complex structure as well. So how would you find the XOR of this remaining component? So we can use the property of XOR here. Let's say T is the total XOR of this entire subtree, and XOR of this entire subtree would be A XOR B XOR C, right? Because A is the XOR of this particular subtree, B is the XOR of this particular subtree, and let's say C is the XOR of the remaining piece. So T would be equals to A XOR B XOR C. Now we know that A XOR A is actually equals to 0, right? So what we can, like we can utilize this and we can just do a XOR of A XOR B on the both side. Okay, so just do A XOR B on both side. So if you do A or B on the both side, this A and this A will be cancelled out, and this B and this B will be cancelled out. Basically, they will be 0, and 0 dot C will be C. So in a way, what you get is C equals to T XOR A XOR B, right? So that's what you get. So you hope you get what how to find out the value of the third piece, which is C. The XOR of this component, the third component is C. You find out the XOR of this entire tree, which is T, like that is just one time computation. You find out the XOR, and then you just do XOR A and XOR B, where A and B are the XORs of two components that you have figured out because they are pure subtrees. So that's how you will compute the XOR of C. Now this is one particular case. Like after computing XOR A and B, after computing the XORs of three components A, B, and C, you can easily find out the score by just taking the maximum and minimum and subtracting them. Now this is one configuration. There can be other configuration as well. For example, let's say you remove these these two nodes. Okay, so if you remove these two nodes, the first component would be this. Okay, and second component would be this, and third component is this entire piece. Okay, so now what we are seeing here is we don't have this, like previously we find out the XOR of this complex piece C by doing the XOR of entire tree with A and B. Now here we can get the value of A because A again is a pure subtree rooted at 5. But how to get the value of B? B is again a complex structure, right? How to get the value of B now? So if you look closely, B is not a complex structure. Instead, it's just entire subtree with some pieces remove. So if like this 2 is entire subtree with just one piece removed, which is 5. So you can find out the XOR of this B, like you can find out B as well by the same trick. What you can do, you know the XOR of this entire subtree. Let's say the XOR is x2. Okay, you can just XOR it with XOR of 5. So in a way, you will get the value of B. How? XOR of 2 contains the XOR of this entire tree, which will contain 5, 13, 14, all this thing. And if you just XOR it with 5, which contain only 5, 13, 14, 15, 16, again A XOR A is 0. So 5 and 5 will cancel out, 13, 13 can cancel out. So all this will be cancelled out. And what will remain is the XOR of 2, 6, 7, 17, and 18. So that way you can find out the XOR of B pretty easily. So what exactly you have done is we have discussed two kind of cases. One where the two subtrees are not related to each other, like the case like this, wherein the two subtree that is formed or two components that are formed are not related to each other. And for that case, what we have said is we can easily get A, we can easily get B, and by doing T's or A's or B, we will get the XOR of this entire rest over the rest pieces. And second case that we have discussed is the case wherein these two components are actually a part of the same subtree. So the first component is this, and second component is this. So how to find out the score or basically XOR of these three components? Again, XOR of first is x of 5 clearly, and XOR of second component, which is B, is actually equals to x of 5 XOR x of 2, because x of 2 will contain the XOR of this entire subtree of 2, and x of 5 will contain the XOR of this entire subtree of 5. If you just do a XOR, you will get the XOR of this remaining pieces. That's what you want. And third piece, as usual, you will find out by doing T XOR A XOR B. So hope you get what we are trying to do. Now, an important point, like we are able to find out the value or the score of a particular configuration in order one time, and hence for all n square possible combination we will be having order one time to compute this particular like to compute the score of a particular configuration. Now once, like what you have to do is you get you get the entire piece, like basically you have the two cases. First case where the two edges that you have chosen is not a subtree, and for that you know what to do. And for second case where they are subtree. So for every combination you need one more answer, whether they are a ancestor of each other or not, right? So that's what you also want. So whether they are ancestor of each other or not. So if they are ancestor of each other, you know the XOR of say the bigger one, the parent one would be the, like you have to XOR it with the children one to get the actual value of B. Otherwise, if they are not ancestor, B would be x of 2, like let's say this one and this edge. So and A would be x of 4. But if they are ancestor of each other, B would be x of 2 XOR the children one, right? So what we need to find out now is whether given two nodes whether they are ancestor of each other or not. So how to find out ancestor of each other or not? One simple approach could be finding out LCA, but even we don't need to go there. We can do even simpler approach. We are anyway, like in anyway n square is allowed, right? So what you can do, for one you can iterate over the entire subtree and say that okay, ancestor of one, like and you can store a 2D array, and 2D array you will say whether this is an ancestor of this or not. So for one, what you will do, you will iterate over the entire tree and populate this entire tree with, like, to populate this piece with true, right? Similarly, for 2, what you can do, you can mark 2 comma 5, 2 comma 6, 2 comma 7, 2 comma 13 as true. Like, basically you iterate over the entire tree and just mark 2 comma 5, 2 comma 6, 2 comma 7, 2 comma 18, 2 comma 17 as true. So for every node, you will be iterating over the entire over its subtree once and just mark the ancestor. That way you will get a 2D array that will tell you whether A is ancestor of B or not, right? So that way you will get the ancestor, and once you have ancestor, you can easily find out A, B, and C. And once you have A, B, and C, basically the XOR of each component, you can easily find out the score. So let's just quickly look at what we have just discussed. So we need the XOR of a subtree, right? We need, like, we have just started that we will need the XOR of this entire subtree x of 2. We need the XOR of this entire subtree x of 5. So how to calculate XOR? XOR of this x of 5 will be simply XOR of this, and the value of 5. Similarly, XOR of x of 2 will be XOR of 5, XOR of entire subtree of 6, XOR of entire subtree of 7, and then XOR of value of 2. So it's very similar to how you compute sum of a particular subtree. So what we will first do is do a DFS. DFS, we will do DFS and calculate the XOR subtree XOR. So subtree XOR initially is value of source, and then we just XOR it with the subtree XOR of all the children. So for finding the XOR of this entire piece, what we are doing is we already know the XOR of this entire piece, and then we know the XOR of this entire piece. Then we know the XOR of this entire piece. So we drew the XOR of these three pieces and then just XOR it with the value of 2. So that's what we are doing. We initialize with value of 2 and then XOR with each of the children. So this is how we get the XOR. And if you remember, we also need to find out whether A is ancestor of B or not. So that's where we are doing mark ancestor. So what we have done is we have said mark, like, iterate over this entire subtree starting at source and mark everyone as ancestor, like, mark this source as ancestor of every of its children. So in a way, we are iterating over, like, we are doing a DFS again over source, and we are just marking is ancestor of root, like, if source is ancestor of root or not, we are just marking it as true. Now we will do it for every children, and once we have done this, we will have a 2D array that will give us whether A is ancestor of B or not. So we will do this for every source that we will be visiting. So after this DFS, what we have is two things. The XOR of every subtree. Second, we know whether A is ancestor of B or not. Like, we have the 2D array built out. Now this is the main code wherein we will do a DFS, basically find out the XOR of every subtree and mark out the ancestor. Now after that we will iterate over the two edges. So either you can iterate over the edges or you can just iterate over the value. So basically, let's say if you pick 3 and 9. So in a way, what you are saying is the first component is this and second component is this. Sorry, like, basically first first edge is this and second edge is this, and hence first component is this and second component is anywhere that, like, everything is excluding this. Similarly, if you pick, let's say, 3 and 4, you are saying first component, like, you crossed these two edges, and hence first component is this and second component is this. So it's similar if you want to iterate over the edges or want to iterate over the nodes. So I am iterating over the nodes, and we're just checking whether A is ancestor of B or not, or B is ancestor of A or not. If any of this is true, the value of A, like, the value of A, which is the lower piece, the value of B would be A XOR X of I, or X of C1. and C would be total XOR A XOR B. Okay, so after this you will just find out the score. So either they're ancestor of each other, like either of this case you will XOR the value of A with the value of the node of B, and if both the cases are not true, you will do just the XOR. So let's just quickly look at the code to make it more clear. So as discussed, this is like the initialization part. I have kept this G and its ancestor array a global array, so that's where we are initializing it again. We prepare the graph and prepare the values array. Once we have this, we do a DFS, and let's look at the DFS. The DFS is exactly similar to what we have just discussed. Subtree XOR is initialized with the current value, and then we are iterating over each child and just XORing it with the XOR of that particular subtree. After doing this, you can also see we are also marking all the ancestors. So in a way, we are iterating over the entire subtree of SRC, and for every node in the SRC, we are saying that root is an ancestor of every node. So we are iterating over this entire thing, and we are saying that this root is actually an ancestor of all the SRC that we have just visited. So that's where we just populate this particular array. And after that, as discussed, we will iterate over the entire node one by one and check whether A is ancestor of B or not. If yes, the first one is the component one will contain the subtree or of, like, basically we are saying is C2 is ancestor of C1, right? Sorry, C1 is ancestor of C2. So C1 is the lower piece. So basically C1, which is 5, C1 is ancestor of C2. So C2 is 5. So lower piece is 5. This is the first component. So hence component 1 is subtree of XOR of C2, and component 2 is subtree of XOR of C2 XOR C1, like X of C2 and X of C1. And finally component 3 is total XOR and then XOR by component 1 and component 2. So total XOR is subtree XOR of 0, because 0, like I rooted the tree at 0. So that's where the subtree XOR at 0. And finally, after getting all this component, we are just finding out the score of this component. So score function is very similar, like sort the array and just take the difference of smallest and the largest. Similarly, if C1 is ancestor of C2, in that case, sorry, C2 is ancestor of C1, in that case, you will do the just opposite thing. And if none of them are ancestor of each other, then it means they are totally different subtrees. So component 1 will be subtree XOR of C2, subtree XOR of C1, and component 3 will be the XOR of them and the XOR of the total tree. Finally, you will just take the minimum and get the answer. So hope you get the solution. If you have any doubts in this solution, please post them in the comment section below. I would be happy to answer. Now, there's one more thing. Can be other approach as well. Like instead of finding this is ancestor array, right? Like you are finding this ancestor array by marking all the ancestor, because it is order n square. But you can also do, like, implement this is ancestor array with LCA. Like if LCA of x and y is x or not. That's where we say that whether x is ancestor of y or not. So finding out LCA is a different problem. You can easily find LCA in order log n time. Uh, if you want to know how, like, you can just search and you will get a lot of algorithms, like lot of places, lot of explanations about how to find LCA in log n time. If you want me to create a video separately, I would be happy to do that if there are enough interest. So that's all for this video. If you have any doubts, please post them in the question below. And if you like the video, give it a thumbs up. Do subscribe to the channel if you haven't already. Thank you.